Hello everyone, welcome to the chemistry channel. So today we're going to be talking about our third topic in atomic structure called emission spectra. So this is lecture number 3 associated with the atomic structure. So in this lecture we're going to, as I said, be talking a lot about emission spectra. So with that, let's begin. So you may remember from the last video that the wave model of light does not explain some important behaviors that we see. So we said in the last video that the wave model of light does not explain black body radiation. We also said that it does not explain the photoelectric effect. And we also said that it doesn't explain emission spectra. So we talked a lot about these two things in the last video, so we're not going to be talking about these things. So if you have any questions about that, please go back to the previous lecture where I talk a lot about these two concepts. In this video, we're going to be focusing on emission spectra. So with that, let's begin by discussing what emission spectra are. So it all starts with light. So there are actually two types of light, two major types of light that you should be concerned about. The first type of light is called monochromatic light. And monochromatic light means light of a single wavelength. So monochromatic light is light of a single wavelength. And a great example of monochromatic light are lasers. So here I have a red laser beam shooting out. And this red laser beam only consists of red wavelengths of light. So that is an example of monochromatic light. The other major type of light that you should be concerned about is something called polychromatic light. And polychromatic light is light made up of multiple wavelengths. So polychromatic light is light made up of multiple wavelengths. So a great example of this is actually light bulbs. So light bulbs that you have in your house, or lamps, or offices. So here I have a light bulb. So imagine taking a light bulb, allowing that light to go through a slit, so it's nice and focused, and then the light goes into a prism, which then diffracts the light onto this screen here. And whenever you do this at home, and I'm sure you've tried this, whenever you take a prism and put it against a light, you'll see the rainbow form. And this rainbow that you see here are all the different wavelengths contained within this single source of light. And this thing here that is produced is called a spectrum. So this list of wavelengths on the screen here is a spectrum. So a spectrum is the separation of the different wavelengths of light. So the spectrum is the separation of different wavelengths of light. And there's two types of spectra that you should be aware of. The first are continuous spectra. So a continuous spectra is like the one that we see here. There's no breaks in between different wavelengths. They're all continuous. They make one continuous structure. So this is a continuous spectrum. And the next type of spectrum are called non-continuous spectra. So non-continuous spectra are separated by distances. So they only produce certain wavelengths. And here's an example of what a non-continuous spectra would look like. So you see here that you have like a violet wavelength, a green an orange and a red, and they're separated by these distances. So this is a non-continuous spectra. And this non-continuous spectra is actually very important for chemistry. And actually, certain things that you see in everyday life produce these non-continuous spectra. So if you've ever seen a neon sign or a sign that uses fluorescent tubes, these can produce these non-continuous spectra. So in order to show this, I have here a picture of something called a gas tube. So these are gas tubes. I don't know if that's the proper name for them, but that's what we will call them. So this is a box, and inside the box, there's like a little crevice inside the box, and inside that crevice is a tube. And inside the tube, so inside the tube is a gas. So this gas is present inside the tube, and the tube has very low, so this means very low pressure. So you have this tube filled up with this gas, and then what happens is this box is connected to an electrical source. So you would plug it into your outlet, and when you plug it into the outlet, it passes a high voltage. It has a high voltage within this tube. So the box produces a high voltage. And when you turn on the box and the voltage is applied, you'll see that the gas emits a glowing light. And in this box we have hydrogen gas. So whenever you put hydrogen gas inside of these gas tubes connected to these electrical sources, the hydrogen gas will fluoresce or emit a purplish light from the tube. So you'll see purple light emitting from the tube. However, when you put the light being emitted from the tube through a prism, so here we have a prism, the light is transferred through the prism, and put it against the screen, you'll come up with this type of spectra. So this black substance here is the screen, and here we have the non-continuous spectra of hydrogen. And this spectra here is called the line spectrum. And the line spectra is a spectrum with only specific wavelengths. And these specific wavelengths that are produced on this screen are characteristic of the atom or of the element that is being tested. So hydrogen will have a different line spectra than neon. Neon will have a different line spectra than argon. So we can use these line spectra in order to determine the identity of a particular element. However, how do we explain this? How do we explain what elements will produce different types of spectra? How do we predict the spectra that a certain element will produce when we pass a voltage through this? And scientists began to investigate this, and they actually found something called the Rydberg Equation. So Rydberg Equation. So this is the Rydberg Equation. And the Rydberg Equation was actually found to explain the behavior of hydrogen very well. So this Rydberg Equation was found to explain and predict the spectra of hydrogen very well. So let's actually change this to predict and not explain. So predict. So the Rydberg equation was found to predict the behavior of hydrogen very well. And the Rydberg equation is 1 over lambda, which is the wavelength, equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. And this equation was found to predict the behavior of hydrogen very well. So this is the Rydberg equation. And you may be wondering what these different variables mean. RH is known as the Rydberg constant. And the Rydberg constant is equal to 1.096776 times 10 to the 7th meters to the negative 1. And N1 and N2 must be whole number positive integers. Okay? Where N2 is greater than N1. So they knew that this equation could predict the behavior of hydrogen very well. However, they did not know why it could predict the behavior of hydrogen very well. And they didn't know why until a guy named Niels Bohr came around. And Niels Bohr is famous for the Bohr Model. So he's famous for his Bohr model. So recall that we sort of talked about the atomic structure of an atom before. So let's quickly go over that. So remember that we had a nucleus, and the nucleus is positively charged. So that's positively charged. And around the nucleus, orbiting around the nucleus are electrons, and these electrons are negatively, oops, let's get rid of that. I want the pen, so let's redo that. So we'll just do it green again. So this is the electron cloud, and then orbiting around, and these electrons within the cloud have a negative charge. So Bohr had 3 different postulates for his model. Okay? So these 3 postulates were only orbits, of certain radii corresponding to certain energies were allowed. The second postulate is that an electron in an orbit is an allowed state, and if the electron is in an allowed state, it loses no energy. And then the last postulate is that energy is emitted or absorbed only between the transitions from state to state. So those are his 3 postulates. And he stated that the energy emitted or absorbed is equal to H equals HF. So he applied Planck's ideas of the quantization of energy to line spectra. And we're going to go more into all of this later on. So using this model, he derived a very important equation. And this equation allows us to predict the energy associated with a certain energy level inside the atom. And this equation is E equals negative hc RH 1 over n squared. Now, h is the Planck's constant, c is the speed of light, and RH is the Rydberg constant. So this can be simplified, since these all are constants, to E equals negative 2.18 times 10 to the negative 18th joules times 1 over n squared. So this is the equation that you all want to know. So now that we have this equation that can describe the energy associated with a certain energy level, so let's write that. So this equation describes the energy associated with a certain energy level. What can we gather from this equation? Well, the important things to focus on is, the first thing is n. So what is n? N is representative of the energy level of the electron. So it is the energy level of the electron. So it's a possible energy level that the electron could occupy. And n is called the principal quantum number. So n is called the principal quantum number. And n can only be whole numbers. So n can only be equal to 1, 2, 3, 4, all the way up to infinity. So it can only be equal to numbers from 1 to infinity. So from this equation, we can see how n is related to the energy of the energy associated with the electron in that certain energy level. So we can see from this equation that as n increases, the energy of the energy level also increases. So you may be wondering why. Why would an increasing value of n correlate to an increasing value of energy? And it's actually because the fraction here, we have a fraction 1 over n squared. So we have this fraction here. When you increase the value of n in the denominator, you make the value of energy less negative, because remember, the Rydberg constant here, or this constant here in the front of the equation, is a negative value. So when you increase the value of n, you decrease the negativeness of the energy, making the energy more positive and therefore increasing the energy. So that's why increasing the value of n increases the energy associated with that state. And therefore we can say the opposite. As n decreases, the energy must decrease. And down here I have a written form so that you don't have to just go off of what I said. So as n increases, the fraction 1 over n squared decreases, causing energy to be more positive, therefore causing energy to increase. And as n decreases, the fraction 1 over n squared increases, causing energy to be more negative, therefore causing energy to decrease. So that's just the written form of what I just said. Okay? So now that we know how energy and n are related, I have another thing that you should note. And this other thing that you should note is that also as the value of n increases, the orbit radius of the electron increases as well. So you can sort of think of this as a solar system. So here we have the sun, and here we have maybe Mercury, and here's Venus or Earth. So you'll note that as we go farther and farther out into the solar system, the orbit radius of the different planets increases. So as we go from the sun outward, we see an increasing radius. So therefore, the orbit radius of Mercury is less than the orbit radius of Venus, and Venus has a smaller orbit radius than Earth, etc. So you can sort of think of this, you can sort of apply this idea to the atom, where the sun could be analogous to the proton, to the nucleus, and the planets could be analogous to the electrons. And as the energy levels, so we can maybe call this orbit n equals 1 and this orbit n equals 2. So as the value of n increases, the orbit radius increases as well. So that's a very important thing to know. Okay, so it is important to note that in the H atom, the electrons can occupy any of the orbits. So it can occupy the n equals 1, 2, 3, 4, 10, etc. So it can occupy any of these energy level orbits. However, in order to occupy these orbits, the electron must obtain or release enough energy. So in order to be in these different energy levels, the electron must contain the proper amount of energy. So the amount of energy that an electron has determines its position in the atom. So we can classify the positions of electrons on the ground state or being in the excited state. When an electron is in the ground state, it is in the lowest energy state. So you can call the ground state as the most stable state. Or when an electron gains energy, it can be in a higher energy state. So we're going to get more into this a little bit later into the lecture. So how can we jump from the ground state to an excited state? In other words, how can we jump from a lower energy level to a higher energy level, or from a higher energy level to a lower energy level? And the answer is by absorbing or emitting energy. So in order to understand this, I have sort of the jumping analogy again. So say here we have a superhero and he can fly really high. So imagine that we have the ground level and this really high step, and this high step is 10 meters tall. So let's say our superhero starts from a potential energy value equal to 0. So he's on the ground, his potential energy is equal to 0. But say, however, he wants to jump from the ground all the way up to the top of this building here. This building is 10 meters tall. Therefore, the top of this building has a greater amount of potential energy than the ground because it has a height of 10 meters. Therefore, its potential energy would be equal to mg times 10 meters. So once the superhero jumps from here all the way up to here, he'll have a much higher potential energy. Therefore, on the ground, our superhero is considered to be in the ground state. However, when he flies up, all the way up to the top of the building here, his potential energy is much greater because he's much higher off the ground. However, to get from the ground state to the excited state, he has to absorb a certain amount of energy in order to be transferred from this low state to the high state. And this certain amount of energy is equal to the difference in the potential energy between the ground state, so we'll call it the ground, and the potential energy of the excited state. So the amount of energy he must absorb is equal to the difference between the excited state and the ground state in this case. Or if he wants to jump from the top to the bottom, the difference in energy would be the potential energy being emitted from him. So in this case, when he jumps down, the change in energy would be equal to P of the ground state. So I'm sorry about that. Let's change that. So the change in energy would be characterized by the potential energy associated with the ground state minus the potential energy associated with the excited state. So therefore, in order to jump from the lower level to the higher level, he has to absorb a certain amount of energy. And in order to jump from the higher level to the lower level, he has to emit a certain amount of energy. And that is the basic idea that you need to know. In order to jump from a lower energy level to a higher energy level, you need to absorb a certain amount of energy. In order to jump from a higher level to a lower level, you need to emit a certain amount of energy. And this can be applied to electrons. Therefore, Niels Bohr came up with this equation, that the difference in energy levels, the difference between the two energy levels, is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n2 squared minus 1 over n1 squared. So where n2 in this case is equal to the final state and n1 is equal to the initial state. So this equation will give you the difference in energy between two states. So therefore, from this equation, we can understand some different things. So if n2 is greater than n1, then what happens is the energy level, the change in energy, is positive. And that's because if n2 is greater than n1, this fraction would be smaller than this fraction, causing it to be a negative number. However, if the negative number is multiplied by another negative number, you get positive. And this also makes sense because if the final state is a higher energy than the initial state, so if the final state is higher in energy than the initial state, the electron would have to absorb energy. So delta E would be positive, and energy is absorbed. However, the opposite is true as well. If n2, or the final state, is less than n1, the initial state, then delta E is negative and energy is emitted. And energy is emitted, okay? All right, so I have a little visualization here in order to show the difference between the two processes. So the first thing we're going to look at is an absorption. So what if I want to take this electron, so this symbolizes an electron, and move it to the N2 level, so from the N1 to the N2 level. This energy level is lower than the N2 level. So therefore, in order to go from a lower energy level, so this is a lower, to a higher energy level, what I need to do is absorb a certain amount of energy, and this energy can actually be carried by light. Because remember that E is equal to hf. And therefore, in order to jump from N1 to N2, this electron needs to absorb the correct amount of energy. In this case, it would be the energy difference between N1 and N2 in order to jump from N1 and N2. So in this case, the energy absorbed would be equal to the energy difference. So the energy difference between N1 and N2. So the energy difference between N1 and N2, so this means the energy difference between N1 and N2, would have to be equal to this incoming light. So the incoming light, in order for this jump to occur, must be equal to the energy difference between N1 and N2. So when it absorbs this correct amount of energy, the electron can move from N1 to N2. So therefore you have an absorption. Absorption. So the next type of energy transition is an emission. So emissions occur when a electron moves from a high energy level to a low energy level. So in this case, when the electron goes from the n equals 2 to n equals 1, light will be emitted. And this light that is emitted will be equal to the energy difference between N1 and N2. So this emission of energy will cause the electron to drop from the n equals 2 to the n equals 1 level. And this is called emission. So in absorption, you absorb light / energy, and this, in order to jump from the lower energy level to the higher energy level, you need to absorb the same amount of energy from the light that is equal to the energy difference between the two levels. So the energy of the incoming light must be equal to the energy difference between the two levels in order for it to jump from a lower level to a higher level. And in order to jump from a higher level to a lower level, the energy is released, and this energy is equal to the energy difference between the two levels. Okay, so let's now talk about how we can apply this change in energy to the wavelength of light. So we can relate the change in energy to the wavelength of incoming light. And that's because, remember, E equals hc over lambda. Therefore, the energy of photons can cause transitions between energy levels. So the only requirement for these photons is to have the same amount of energy as the energy difference between the two levels. So we can derive an equation that relates lambda, or wavelength, to the energy transitions. So we start off with the equation that Bohr gave us. So delta E is equal to negative 2.18 times 10 to the negative 18th joules times 1 over n final squared, so I'm just going to use final, minus 1 over n initial squared. So we know that this part here, this constant, is equal to negative hc times the Rydberg constant over 1 over nf squared minus 1 over ni squared. And we know that delta E, in order for this transition to occur, the energy of the incoming light must be equal to this difference in energy. So therefore, this can be set equal to hc over lambda. So you'll notice that we have some common factors here, so we can cancel these two factors out. This therefore gives us 1 over lambda equals negative RH 1 over nf squared minus 1 over ni squared. And now what we can do in order to get lambda to the numerator is we'll just take the inverse of the whole function, giving us lambda is equal to negative RH times 1 over nf squared minus 1 over ni squared, all to the negative 1. So this is our equation. So I'm just going to put it in here as well. So this is the equation you want to know. So that is the equation that you want to know. Okay? Okay, so from these topics that we just talked about, we can summarize what we learned in this segment here. So therefore, if electrons absorb light, they can move from a lower state to a higher state. However, the incoming light must be equal to the energy difference between the two states. And if electrons emit light, they can move from a higher state to a lower state. And the light that they emit has an energy equal to the energy difference between the two states. So this sort of summarizes what we discussed up to this point. So one of the last little topics I have here is an important thing to know. So this important thing to know is the separation of energy levels. And it's important to note that as the value of n increases, the difference between the values of energy tends to decrease. So what does this mean? So let's say we have the energy difference between n equals 1 to n equals 2. We can measure it like so. If you then measured the energy difference between n equals 4 and n equals 5, you notice that the energy difference is much smaller between these two levels. And that's because as you increase the value of n, as you increase the value of n, the differences between the energy levels decrease. So therefore, as you go up in the energy levels, you'll notice that the energy levels are written closer together. And that's because the differences in energy decrease as we go up in energy levels. So the last thing to note is the limitations of the Bohr model. So the Bohr model explains one electron species well, but not multi-electron species. So the limitation of the Bohr model is that it can only explain one electron species. So it can explain hydrogen ions, you can do helium plus, and so on. So as long as you have one electron, the Bohr model explains the behavior pretty well. However, when you start adding more than one electron, the Bohr model fails. And we won't address multi-electrons until we get into further section in atomic structure. So that is it for the concepts for today. And to end off, I have three practice questions for you. So I have 3 different practice questions for you. And I encourage you to try them by yourself. And when you're done, you can restart the video, and you can start the video and see if you got them right. So with that, let's begin. So the first question asks you to calculate the energy change from n equals 1 to n equals 4 and state whether energy was absorbed or released. Now, in order to figure this question out, all you have to do is do a plug and chug. So you would just use this equation, and you would put for the 1 over, and this would be equal to negative 2.18 times 10 to the negative 18th joules times 1 over 4 squared, because that's the final state, minus 1 over 1 squared, the initial state. And when you plug this in your calculator and conserving the amount of sig figs, so in this case 3, delta E would be equal to 2.04 times 10 to the negative 18th joules. Oops, let's actually fix that. Okay. And now, is energy absorbed or emitted? Well, even before doing the calculations, you should be able to answer this. It's absorbing energy because in order to go from a lower energy level to a higher energy level, you need to absorb energy. And delta E is positive in this case, so we absorb energy. So the next question asks you, what is the energy associated with the energy level of infinity? So remember that our energy equation, so the energy associated with an energy level is equal to negative 2.18 times 10 to the negative 18th joules times 1 over n squared. So that is the equation that you need to know. And you'll notice here that n in this case is in the denominator, and this infinity is talking about n. And if you put infinity in the denominator, you'll notice that this sort of forms a limit. So we can express this as a limit. So what this is saying is that as x goes to infinity, the value of this equation approaches 0. So when n is equal to infinity, the energy associated with that energy level is equal to 0. And in fact, this energy level at infinity is referred to as the reference energy. And that's because it has 0 energy. And at the reference energy, the electron is dissociated from the atom. So this is the reference energy level. And now the last question I ask you, which transition will emit the shortest, this should be the shortest wavelength of light. Now remember that E is equal to hc over lambda. Therefore, the shortest wavelength will have the highest, so this should be energy difference, should have the highest energy difference. So therefore, we're going to first look to see which one is an emission and which ones are absorption. So we can already cancel choice B out because going from n equals 4 to n equals 5 is an absorption. So now we're left with A, C, and D. Now, we also know that as we increase in the value of n, so let's straighten this out here. So as we increase in our value of n, the difference between the energy levels decreases. So this n equals 8 to n equals 7 compared to these two will be a lot smaller than the energy levels associated with C and D. And we know that the n equals 2 and the n equals 1 is the greatest distance, so therefore it will emit the greatest amount of energy and the shortest wavelength. So the answer is C. And that concludes this video. I thank you guys for watching, and in the next video we're going to continue with our series of lectures on atomic structure. This is all very important, it's all fascinating, so I want to thank you all for watching, and I hope to see you next time.